This is part 2 of our video series on how handheld XRF decreases the time required to ID and source physical contaminants found in manufactured foods. In this video, we will explain how to identify and source contaminants for complex situations. These arise when there are multiple potential sources of the contaminant. Our objective is to provide you with information to ID and source contaminants. We will first review potential sources of physical contaminants and the simple alloy grade ID method. We will then explain how to use the spectral fingerprinting method to ID and source contaminants. We will explain best practices in creating a production floor spectral fingerprint library. We will provide best practices in identifying metal contaminants with spectral fingerprint matching. And we will demonstrate the use of RTAC spectral fingerprint matching software to perform this method. Do you remember the most common physical contaminants found in manufactured food products? They are slivers of metal, bits of plastic or rubber, small shards of glass, and even chips of stone or ceramic. Do you remember how even very small pieces of metal can be identified with handheld XRF analyzers? A found metal object can be identified with XRF by determining its composition, the type of alloy it is, and the alloy grade name. Remember, there are only 4 simple steps to ID metal contaminants with handheld XRF. First, you prepare the piece of metal in a way that XRF can see it. Then, you select the alloys application on the Ready to Test screen. You position the found object to the XRF's window view, and then you start the test, and then view the results on the screen. In this case, it's 316 stainless. Do you remember how XRF identifies a metal contaminant's alloy grade? Alloy grades are defined based on their chemical composition, essentially which elements they contain and at what concentrations. Handheld XRFs can be configured with an alloy calibration, which determines the sample's composition and has libraries with predefined alloy grades, including their minimum and maximum limits. An unknown metal is identified based on comparing its measured composition to those stored in the alloy grade libraries. The grade libraries on board the handheld XRF with the alloy calibration are extensive. There are hundreds of grade definitions which cover multiple international standards. Users can select libraries including UNS, DIN numbers, and other standards. They cover multiple classes of alloys, including those listed. But what happens if the metal contaminant you ID'd as 316 stainless steel could be from more than one source on your production floor? What if your auger, conveyor, grinder, mixer, roller mill, and sorter are all made of 316 stainless? Well, the procedure to source the contaminant is a bit more complex. It's important to be familiar with the alloys used for food production equipment. They provide important characteristics for sanitation and for protection from corrosive foods, high temperatures, moisture, and pressure. So if you have identified the contaminant as a particular alloy, and there is more than one possible source, how do you use the handheld XRF to help you find the actual source? When you test the metal contaminant, the answer appears on the handheld XRF screen. Remember, it's given in the form of the identification of the alloy, the list of the elements identified, their concentrations, the minimum and maximum concentration of each element for the identified alloy grade from the library, and the measurement's accuracy. It also provides you with a spectrum or spectral fingerprint of the contaminant. Do you remember how the data processor views the elements as a spectra? If the element is in the sample, the detector sees its energy signature along the x-axis. It can also tell how much of each element is in the sample using the height of its peak along the y-axis. The contaminant has a spectral fingerprint which can be used to match it to its source. This identification is made by comparing it to a library of reference spectra, essentially the fingerprints of all the alloys used on a production line. Fingerprinting is very selective and can differentiate similar samples better than alloy grade ID can. It works well for very small samples, even down to 1 millimeter in size. It works for all types of materials, including metals, plastics, and ceramics. but it is more complicated to use than the simple alloy grade ID program. There are 3 primary stages required to optimally use the more complex alloy spectral fingerprint ID method. The first one is to create a food contact material library. This stage takes a significant amount of time to set up because you need to create a spectral fingerprint library of all food contact devices and components for a given production line. But once it's done, sourcing a contaminant is fast, and the library can be edited whenever there are changes on the line. Before you even start taking tests, you need to set up a spectral fingerprint data library system on a PC. Here's an example. First, in your Documents folder, create a main folder for all the test data you will be taking. Next, create a subfolder for each of the production lines on your floor. For instance, if you have 5 production lines on your floor, create a production line folder for each one. Then, create subfolders for both process equipment libraries and for physical contaminant tests within each production line folder. You can set up folders for metal contaminants, plastic contaminants, a metal process equipment library, and a plastic process equipment library for each production line. Now you need to determine a naming convention for each piece of process equipment you will test to store its spectral fingerprint in the library. For instance, you could use names like air deflector cooked production cooler, Part C tempered wheat screw conveyor, shingle cooked production cooler, or skin A continuous cooker. The naming convention needs to make sense to your particular production line. Finally, you need to test each piece of process equipment and store its spectral fingerprint in the correct folder. For instance, if you test a metal piece on production line A, you need to name it and place it in the process equipment library metals folder. Once you've created your spectral fingerprint library, you are ready to identify the source of contaminants that are found during production. The next stage in using spectral fingerprint matching is to test the found contaminant. This just takes a few moments. Remember from the first video, you isolate and clean the contaminant. If it's a small one as pictured here, it's recommended to sandwich the sample with thin film and then place it in an XRF sample cup. Using the handheld XRF in a desktop stand, you then place the sample cup on the analyzer window. The integrated camera helps assure your positioning of the sample. The PC software which comes with the handheld XRF can be used to control the instrument to perform the test. You simply close the cover and select Start to get your results. Once the data has been collected, you then need to name the contaminant and transfer its spectra to the correct folder in your production line library. If you found it on production line A, you would then save it to that line's metal contaminants folder. The final stage in using spectral fingerprint matching is to compare the spectral fingerprint of the metal contaminant to the spectral fingerprints of all the metal equipment in the production line folder. This can take up to 5 minutes, but it significantly decreases the time needed to determine if a metal contaminant is from the production line or not, and if so, its source. Spectral fingerprint matching for the more complex contaminant identification situation, which arises when there are multiple potential sources of the contaminant on the production floor, is performed with Bruker's RTAX PC software. RTAX is an advanced spectral viewing, matching, and data analysis software package. It is used to both store and link information. RTAX makes the management of large data sets, like food production spectral fingerprint libraries, easy. After the spectral fingerprint folders for a given production line are populated with data, those folders are transferred into an RTAX project folder. These are used as a library reference set to identify a found physical contaminant. On the left-hand side of the RTAX window, you can see the folders of all the metal equipment spectral fingerprints from a particular production line placed into the RTAX project folder. And on the right-hand side is an image of multiple spectra, each identified by an individual color. The contaminant spectral fingerprint folder is then transferred to the same project folder, which contains all the possible sources on that production line. In the upper left-hand corner, you can see the spectral fingerprint contaminant's name. On the right-hand side of the RTAX window, you can see its spectra. The fingerprint spectra is then analyzed using the RTAX match program to find the most likely source of the contaminant in that project folder. In the case below, RTAX found 100 hits with a correlation of 90% or better. One RTAX match hit had a correlation of 99.99%. That hit is highlighted in blue, and you can see it is identified as Scraper Mill 012 at 130.617_121534. Let's take a closer look at this match. Since identifying the source of a physical contaminant is critical, it is best practice to confirm RTAX spectral matching results with a visual comparison. This is done by first overlaying the contaminant spectra on top of the closest matching library spectra. In this case, it's the one that is 99.9% matched, the Scraper Mill piece. Let's zoom in on the spectra from around 6 to 7 keV, which is where the iron K-alpha and K-beta energy signals are. Although the peaks line up at the same keV energies, the contaminant spectra peaks are not as high as the library spectra of the match source. This is because the contaminant is so much smaller in size than the sourced equipment that was measured. There was not as much surface area to measure as there was with the original food contact material test. RTAX has a normalize function which will bring spectra of different size samples to the same scale to help confirm a visual comparison. You simply select Normalize in the spectrum matching software and can see that the spectra of the Scraper Mill source lines up perfectly with the contaminant. Finally, it is straightforward to copy and paste the RTAX spectral matching information to Windows programs for reporting purposes. In this case, the top 3 matches are identified and listed with their correlation percentages. You can customize this as needed. In summary, contaminant identification for food production is critical, and handheld XRF decreases the time required to ID and source physical contaminants found in manufactured foods. This video explained how to identify and source contaminants using spectral fingerprinting, which is very selective and can differentiate similar samples better than the standard alloy grade ID method can. There are 3 primary stages for this method. The first one is to create a food contact material library. The second one is to measure the food contaminant. The final one is to identify the source of the food contaminant using Bruker's RTAX spectral matching software. If your spectral fingerprint library is comprehensive and complete, but you don't find a match, it would be a good idea to inspect supplier starting materials or other sources. Thank you for your time and attention. We appreciate your interest in Bruker's solutions for food safety and quality. If you would like more information, a budgetary quote, or to set up a demonstration at your facility, please call us at 1-509-736-2999 or email us at sales.hmp@bruker.com. Thank you again.